Imagine you have two identical wooden crates. Fill both with the exact same type of oranges, and you might expect them to weigh the same. But depending entirely on how those oranges settle and pack together inside the crates, one could end up significantly heavier than the other. We can think about solid materials the exact same way. In this analogy, the oranges are individual atoms, and the wooden crate is what engineers call a unit cell. A unit cell is the smallest repeating geometric building block of a material. Every solid metal you interact with is essentially made of millions of these identical microscopic boxes stacked together in a three-dimensional grid. But because atoms are spherical, they can never fit together perfectly. No matter how tightly you press them against each other, there will always be empty gaps left over between the curves. Because of these gaps, nature has to arrange atoms in specific patterns to create a solid object. This leads to a central question. How efficiently can these spherical atoms actually be packed into a given space? Understanding the answer to that question reveals the secret to why different materials have different physical properties, like their weight and their strength. Nature has a few specific, repeatable ways of organizing these atoms inside our unit cells, which we categorize as crystal structures. This diagram shows what we call a simple cubic structure. As you can see, the atoms sit perfectly at the 8 corners of the box, which leaves a rather large void of empty space right in the middle. Looking at the next rows in this table, we see tighter ways to pack. Body-centered cubic, or BCC, places an extra atom in the center. Face-centered cubic, FCC, places atoms on the flat sides, fitting more matter into the same space. To measure exactly how tight these arrangements are, engineers use the formula shown here in this green box, called the atomic packing factor, or APF. The APF is simply the total volume of atoms inside a unit cell, divided by the volume of the box itself. For the tighter face-centered arrangement, it calculates to 0.74. This means 74% is solid matter, and 26% is empty air. The APF takes a complex, three-dimensional microscopic arrangement and turns it into a simple percentage. With that percentage, we can begin to calculate density. Once we know how full our atomic box is, we can shift our focus from volume to mass and figure out how heavy the box is. This is where theoretical density comes in. Engineers can accurately calculate the weight of a solid metal block using math without needing a physical scale. This visual shows the theoretical density formula. Let's look at the individual pieces to see how it works. In the top half of the equation, the letter N represents the number of atoms. Going back to our analogy, this is simply the count of how many oranges fit perfectly inside one unit cell box. Right next to it, the A stands for atomic weight. This represents the specific weight of one individual atom. By multiplying the total number of atoms by the weight of a single atom, the entire top half of the equation simply gives us the total mass sitting inside our microscopic box. Moving to the bottom half, V sub C is the volume of the unit cell. This is the literal physical dimension of the box itself, its microscopic length, width, and height. Finally, we multiply that volume by NA. This is a mandatory scaling factor known as Avogadro's number. Think of it as a scientific bridge connecting the tiny world of atoms to our human scale. This bridge is necessary to translate the weight of a single atom, which is too small for us to even feel, into standard grams that we can actually use in the real world. By combining the physical arrangement of the atoms with this specific formula, the physical mass of any material in the world becomes perfectly predictable. Now that you have the pieces, take a look at your lecture notes. Try calculating the theoretical density for nickel or copper yourself to prove the math works.